Hi students, in this session we are going to discuss the concept of inverse function. I hope all of you are ready with pen and paper. See, before going to inverse function, we need to recall some functions. So let's get started. Consider function f. Consider function f from a to b. Here, suppose set A contains elements 1, 2, 3 and set B contains elements 2, 4, 6, and by function f 1 is related to 2, 2 is related to 4, 3 is related to 6. And consider one other function g from x to y. Let set X contains elements 1, 2, 3, 4 and set Y contains elements A, B, C. This is set Y and here it is function G. Here 1 is related to A, 2 is also related to A, 3 is related to B and this 4 is related to C. See, observe these two examples here. We here observe that here 1 is related to 2. That means 2 is image of only one element. Similarly, 4 is image of only 2. 6 is image of only 3. That means here we observe that distinct elements in the domain have distinct images in the codomain. And here in this case, in this example, see A is image of two elements. Image of 1 is A, image of 2 is also A. That means two elements have same image. So these two are two different examples. See here, different elements in the domain are related to two distinct elements in the codomain. So such type of functions are called one-one function. And if it is not like this, then such type of function is called many to one function. Okay, so let's see definition. See, one function, or it is also called as injective function. See, a real valued function f from a to b is called one or injective function if distinct elements in A, that means in domain, have distinct images in B. That means in codomain, elements in A have, from domain have distinct images. That means, see, for x1, x2 belonging to A, that is domain, such that x1 is not equals to x2, that is, these x1 and x2 are two different elements. That implies their images are different. That means f of x1 is not equals to f of x2. And otherwise, the function is many one function. Okay. So keep in mind, if for a function distinct elements in the domain have distinct images in codomain, then the function is one or injective function. Okay, let's see one more example. See, let us consider function f of x is equal to 2x plus 3 for x belonging to R. That means for this function, domain set is set of real numbers. Now we have to decide whether this function is one or not. For this, see, in this example, it is easy to see these three elements are there in the domain only. So it's easy to see their images. But for this function, we have to use some technique. So see, for some elements x1, x2 belonging to R, if we consider f of x1 is equal to f of x2, then that will imply, see, f of x1 is 2x1 plus 3 is equal to f of x2 is, see, twice of x2 plus 3. 3 get cancelled on both sides. So this implies twice of x1 is equal to twice of x2. So this implies x1 is equal to x2. See, here for f of x1 is equal to f of x2, we get x1 and x2 are same elements in the domain. That means there are no elements which have same images. So for this function, distinct elements in domain have distinct images in the codomain. So this given function is a 1-1 function. Now see one more example. Suppose g of x is equal to x square plus 1. For x belonging to R, that means R is a set of real numbers and which is domain for this function. So here we just observe that if we find g of 1, then it is 1 square plus 1 is equal to 2, and for g of minus 1, see, it is again, see, minus 1 square is 1, 1 plus 1 is 2. So two elements have same image. Two elements, that means element 1 and element minus 1 have same image. So this function g of x is not 1-1 function, it is many to one function. Okay. So students, see, this 1-1 function or injective function is very simple concept and it is very easy to understand. You have to just remember that distinct elements in the domain have distinct images in codomain. That is what for injective or 1-1 function. Now students, let's move on to next concept. For this, consider function f from a to b and consider set A containing elements a, b, c, d and set B containing elements 4, 5, 6. And under function f, if A is related to 4, B is related to 6, C is related to 5, D is related to 5. Observe here that all the elements in the codomain are images of some elements in domain set. That means here for function f, range set is equal to codomain set. Okay. So such type of function is called onto function. Onto function or surjective function. So let's see definition of onto function or surjective function. A real valued function f from a to b is said to be onto or surjective function if every element of b, that means codomain, is the image of some element of a, that is domain. Okay, under function f. That is, if f is onto, then range of f is equal to codomain of f. Let's see one more example. Consider function f from n to n and it is defined by f of x is equal to 2x. See, this function is 1-1 function. How it is? For x1, x2 belonging to n, if we consider f of x1 is equal to f of x2, this implies twice of x1 is equal to twice of x2 and therefore x1 is equal to x2. That means two elements are same from domain and their images are also same. So function is 1-1 function. Now what about function to be onto? Okay, So here we observe that 1 belongs to n and there does not exist any natural number for which f of x is equal to 2x. Okay, 1 is not twice of any natural number. So this function is not onto function. Okay, this is not onto function. That means this function f from n to n defined by f of x is equal to 2x is one function, but it is not onto function. If we define this function from instead of n to n, if we define it as r to r, then it will be 1 and also onto function. Okay. See how for any real number y, for any real number y, there exists x is equal to y by 2 belonging to r such that f of x is equal to f of y by 2. So this is y by 2 into 2 is equal to y. That means there exists x belonging to r for which f of x is equal to y. So every element in R is image of element in domain R. So if we define this function f from R to R, this function f of x is equal to 2x, then this function is 1 and onto. And here comes next concept, that is bijective function. See, when function is 1 and onto both, then that function is called bijective function. So this function f from R to R defined by f of x is equal to 2x is a bijective function. See definition: bijective function, a function f from a to b is said to be bijective function if f is both 1 and onto, that is injective and surjective. If function is both injective and surjective, then it is called as bijective function. Students, next we want to discuss is identity function. See, identity function is again very simple concept. Let's see definition. A function f from R to R where f of x is equal to x for all x belonging to R is called identity function. See, function f of x is equal to x for all x belonging to R is an identity function. Very simple concept. If we consider this function as y is equal to f of x, then it is like y is equal to x. And see, this is familiar equation to us. Y is equal to x is nothing but a line passing through origin making an angle of 45 degree with positive x-axis. Okay, so if we think of graph of this function, how to plot graph of function, we consider the ordered pairs x comma f of x, and for all such ordered pairs we get smooth graph of that function. So one interesting thing about this identity function is graph of this equation is a straight line passing through origin, and this line makes an angle of 45 degree with positive x-axis. See this line passing through origin making an angle of 45 degree with positive x-axis. So this is identity function. Let's see example of identity function. For this, consider function f from R to R defined by f of x is equal to 2x plus 3 And consider function g from R to R given by g of x is equal to x minus 3 upon 2. For these two functions, let's find their composition of f and g. So gof of x. For the composite functions, you can find link in the description. So let's find gof of x. So this is nothing but g of f of x, and this is g of, we have f of x as 2x plus 3, and so g of 2x plus 3 is, see, we have g of x is equal to x minus 3 by 2. You put for x 2x plus 3, so this is 2x plus 3 minus 3 upon 2. So this is 3 get cancelled, 2x upon 2, so this is just x. So we have gof of x is equal to x. See here, you can easily observe that this gof function is identity function in this case. Okay, now let's find fog of x, composition of g and f. Fog of x is, see, f of g of x, and we have g of x as x minus 3 by 2. X minus 3 by 2. Now f of x minus 3 by 2 is, substitute x minus 3 by 2 here in 2x plus 3. So we have 2 into x minus 3 by 2 plus 3 plus 3. So this 2 get cancelled and we have x minus 3 plus 3. So this is x. That means fog of x is equal to x. Again, here we observe that this fog of x is an identity function. So here we observe that for the function f and g, here their compositions gof of x and fog of x are identity functions, and you can easily observe that these two functions are one and onto, that is bijective functions. So here f and g are called inverse functions of each other, are called inverse functions of each other. See, these two functions are bijective, that is one and onto, and gof of x and fog of x are identity functions. In this case, f and g are called inverse functions of each other. Let's see definition of inverse function. Inverse function: if f from a to b and g from b to a are one and onto functions such that gof from a to a and fog from b to b are both identity functions, that is gof of x is equal to x and fog of y is equal to y, then f and g are called inverse functions of each other. Just in the above example, we find that function f and g are inverse functions of each other. And inverse of function f is denoted by, see this notation, f, you write it as f raised to minus 1 and it is read as f inverse. Don't confuse with this notation, since we in rules of indices we use, if we use a raised to minus 1, in that case it is 1 upon a, but here f inverse is not 1 upon f, it is just symbol to denote inverse function. So don't confuse with these concepts. Okay, f inverse is just notation to denote inverse of a function. It is not like 1 upon f. Okay, it is just a symbol to denote inverse function. And inverse of function g is denoted by g inverse. You write it as g raised to minus 1, but it is not the power, it is just symbol to denote inverse function. So we define a function f inverse from b to a such that if f of x is equal to y, then f inverse of y is equal to x. Here also you note that domain of f is equal to range of f inverse, and range of f is domain of f inverse. Student, if inverse of function f exists, then function f is called invertible function. Invertible function. Here we say that if function is invertible, then it must be 1 1 and onto 1 1 and onto, and conversely. That means if function 1 1 and onto, then its inverse exists, that is function is invertible. Here, this fact significantly helps us for proving a function f to be invertible by showing that f is 1 1 and onto, especially when the actual inverse of function is not to be determined. Let's see one example. See a function f from R to R defined by f of x is equal to 3x by 5 plus 2 for x belonging to R, and the question is, does the inverse of f exist? So for the existence of inverse of function f, we have to check whether the function is bijective or not. So let's first see whether it is 1 1 or not. For this, let x1 x2 belonging to R such that f of x1 is equal to f of x2. This will imply 3x1 by 5 plus 2 is equal to 3x2 by 5 plus 2. This 2 get cancelled on both sides, and then 3x1 by 5 is equal to 3x2 by 5. Again 3 by 5 get cancelled, and we have x1 is equal to x2. That means f of x1 is equal to f of x2 implies x1 is equal to x2. So the function is 1 1 function. Now let's check whether it is onto or not. For this, let y be any real number, then the equation f of x is equal to y implies 3x by 5 plus 2 is equal to y. So see, this equation has unique solution, and that solution is given by x is equal to 5 into y minus 2 upon 3. By shifting the terms, we have this x. So for every y belonging to R, there is x belonging to R, namely x is equal to 5 into y minus 2 by 3 such that f of x is equal to y. So we have function f is onto function. So here function is 1 1 and onto, that is bijective, and therefore f inverse exists. See, f inverse exists. Now see, f inverse of y is equal to x. So this x is given by 5 into y minus 2 by 3, and therefore we have f inverse of x is equal to 5 into x minus 2 by 3. Students, from this example, you observe that how to find inverse of bijective function. So, you equate the given function f of x is equal to y. So, after equating that, you express x in terms of y, and that x is nothing but f inverse of y. So f inverse of y is equal to x, which is completely in terms of y. Then you replace this variable y to get f inverse. Replacing y by x, we get the f inverse of x. So students, this is all about inverse function, and for this we have discussed the concepts one function, onto function, identity function, and then the inverse function. So you go through all these concepts and clear them. So let's end this session. Thank you for watching.